Okay, I guess we can start. Today we are happy to have Biswajit Sahoo, and he is going to speak about trace anomalies, RG flows, and scattering amplitude. Please go ahead.
First of all, let me thank you for inviting me to present a set of works which I did with a set of my collaborators, with some excellent set of people, Denis Karativ, Ian Marucha, Joao Penedones, and Johar Komargoski. So my talk will be kind of based on these three papers, though the main focus will be the paper on the trace anomalies and graviton-dilaton scattering amplitude, but I will also try to describe some applications from boots like S-matrix bootstrap site and some upcoming work on some computational site, or like testing the proposal of this paper too. So let me first start by providing the motivation, like why we use scattering amplitude to study trace anomalies along the RG flow. So first of all, like this trace anomaly is like already a subject like people studied for a long time. It has like a beautiful history and all this stuff, but still we think that if we use like scattering amplitude techniques, maybe we will learn something new, and we will have at least we can learn some non-perturbative aspects of quantum field theory starting from it. So to do that, let me first try to give some insight of what we think a quantum field theory is in modern language. So we think basically quantum field theory is basically renormalization group flow between two fixed points. One is at very high energy and one is at very low energy. And we also assume that these fixed points enjoy some conformal symmetry, so that they are described by some ultraviolet conformal field theory in the high energy and some infrared conformal field theory in the low energy. And at any point on the RG flow, like there may not be a single RG flow like which starts from UV CFT. It can go to many, it can flow to many IR fixed points, but let's consider a single one which is given between two UV and IR CFTs. And then like once someone provides me like what is the UV conform, like UV CFT, and then suppose provides me the relevant deformation which triggers this RG flow, then in principle I can able to study the quantum field theory. Or if there is a spontaneous conformal symmetry breaking, then given the UV CFT and the vacuum expectation value of the corresponding primary operator will be enough in principle to study a quantum field theory. Now, if we want to study like this quantum field theory or this conformal field theory non-perturbatively, what are the available tools from the bootstrap perspective? So obviously, if we want to study the UV CFT, we can use independently conformal bootstrap program. Using this, we can try to find bounds or the allowed regions of spaces in terms of the parameters. The parameters are given by scaling dimensions, operator product expansion coefficients, etc. On the other hand, if we flow to near IR and the low energy, suppose we integrated out all the higher massive degrees of freedom and left out with some light degrees of freedom, there we can use S-matrix bootstrap program, and there we can also bound the spaces of S matrices like using like some parameters, and the parameters basically bounds kind of the masses of the mass ratios of the stable particles, some coupling constant, or some effective field theory parameters. And note that to study various regions of this renormalization group flow, we use different techniques, and different techniques bounds different set of parameters. And in general, like they may not be like, in principle they are related, but in general it could be hard to determine some parameters in the low energy in terms of the high energy parameters. But obviously there are some numerical techniques, and that can be used at any point on the RG flow to study, say, quantum field theory spectrum or scattering amplitude. But all these techniques like lattice field theory, Hamiltonian truncation, or these tensor networks require a kind of introduction of some UV cutoff, and then when we try to extrapolate it to the continuum limit, it turns out to be very costly, and it is very like hard in principle to study like generic quantum field theory. So
sorry, can I ask something?
Sure.
So, like, I'm wondering why for the IR case, so it's still a CFT. Why don't you use well the very same conformal bootstrap?
Yeah, if I am interested just the IR CFT, right, like degrees of freedom, like to study IR CFT, I can use conformal bootstrap. That's true. But suppose I want to probe like what were the degrees of freedom when we flow to the RG, and to probe this kind of degrees of freedom, it turns out to be useful to like use asymmetric bootstrap program. Basically, I agree that yeah, maybe if we had exactly seated IR CFT, we can use actually really CFT bootstrap program to bound the space of CFT, which is like the UV CFT in general. But if we are at some energy scale where still there are some like massive particles are there in the spectrum which are possibly light, and then we can use asymmetric bootstrap program like the unitarity and some high energy some boundedness, and can study this thing. But in the I think the question which I want to ask is that these two parameter space are different, and given suppose if I study say only IR CFT using conformal bootstrap, I may not able to know that or that won't tell me anything about the from which UV CFT it can flow to that space of IR CFT. So the question I want to understand is like the full RG flow, or try to find some non-perturbative understanding of the full RG flow even from the low energy perspective.
Okay, and can you use S-matrix bootstrap for any point on the RG flow?
I can use asymmetric bootstrap. Yeah, if this is like if like there are asymptotic states, I can use in principle at any point on the RG flow. But what happens is that if I go a little bit above, like suppose there is a mass gap in the QFT, and if I suppose go far above this energy scale and there are multiple particles, then it turns out to be numerically very challenging in presence of multiple set of particles to use a asymmetric bootstrap program. So it is always easier when there are few asymptotic states, but not many.
Okay, thank you.
So yeah, so now the question we want to ask is that, can we identify a set of observables in the low energy, like as a low energy expansion of that observable, which suppose completely determined by the UV CFT and the IR CFT data, and completely independent of the RG flow. Okay, so then possibly if we can identify such kind of observables which are completely determined by the UV and IR data, then possibly there is a hope that we can able to find some interrelation between them, or maybe given some IR data we can able to ask this question that from which space of UV CFT it can flow to. So basically we want to first identify those kind of protected observable which are which are kind of independent of how we deform the theory in the UV, or what happens intermediate stages in the RG flow. So this is kind of a broader kind of goal which I am going to describe in this talk. So basically, mathematically speaking, suppose I have like someone has given me a UV CFT, and suppose let's consider for a moment that it's a explicit symmetry, conformal symmetry breaking. So it is broken by introducing some relevant deformation. Now let us introduce a set of background fields corresponding to this relevant deformation operator, and maybe some background fields. So collectively I am denoting those by ji of x. And then this is a suppose strongly coupled RG flow, and we integrated out the massive degrees of freedom and reach the IR. So obviously this massless degrees of freedom like still remains from some IR fixed point. Suppose this is given by some IR CFT, but this IR CFT also could couple to this background fields, and also there will be effective field theory in terms of these background fields which just arises from by integrating out these massive degrees of freedom. Now the question we want to ask is that, given this effective field theory in terms of background fields, can we identify some observables which won't like depend on the details of the RG flow but completely determined by the UV and the IR CFT data? So this is the question we want to ask, or like this is kind of the motivation which we started from. And the goal is that then possibly the hope is that we can able to use some asymmetric bootstrap program starting from this like background field like scattering amplitudes in the IR, and possibly able to probe some UV degrees of freedom, or able to bound the space of UV CFT for a given like QFT spectrum. So the answer in this talk I will try to provide is that we will introduce two set of background fields. One we will call dilaton and another is graviton. And the dilaton will be just a compensator field for the like for the say explicit symmetry breaking in the UV, or this can be also understood as a Goldstone boson for the spontaneous symmetry breaking case. And the graviton field will be just a quanta of the background metric, and we will introduce this background metric so that after compensating by the dilaton, still the theory will be classically Weyl invariant. So we kind of, you can think that we put this UV CFT in a background which is conformally coupled, and then we start deforming the theory, and then the deformation will be compensated by a new field which will be the dilaton. So I'll actually explain all these things in detail. But if we do that, then what we learned is that now if we study, like write down effective field theory in the IR and suppose compute 4 dilaton scattering amplitude, what we observe, okay, it's been observed by Komorowski and Swimmer already, is that the low energy expansion of this 4 dilaton amplitude at 4 power of momenta is completely determined by the difference of the A and A anomaly in the UV and the IR. So a-anomaly is one kind of a trace anomaly, which also can be related as a combination of OP coefficients in the stress tensor correlator of the CFT. Okay. Similarly, what we also observed is that instead of 4 dilaton, if we consider say 2 graviton 2 dilaton scattering, then what we observed is that at 4 power of momenta, it is determined by the completely determined by the difference of the another trace anomaly coefficient, which we call the C trace anomaly coefficient, and also the difference between the A anomaly coefficient between the UV and IR. And the delta N and delta C are given here. Okay, so the UV is the UV anomaly, IR is the IR anomaly, and this delta C is CUV minus CIR similarly. So I will also explain how exactly this C and A appears in the stress tensor correlator in a minute. So once we have this observation, okay, like we introduced background field methods, we computed scattering amplitude, identified some protected observables. Now where can we use those things? So one of the kind of remarkable application is basically proving the A theorem done by Komorowski and Swimmer, where basically they used the unitarity property of this 4 dilaton scattering amplitude to show that this A anomaly coefficient is monotonic along the RG flow. Similarly, we can use the same prescriptions with some given massive spectrum of the QFT. We can also able to bound the value of the UV CFT A anomaly value for a like spectrum of QFT, and like we can able to bound that, okay, like given a massive or gapped QFT, what will be the space of the CFTs which can flow to a gapped QFT. So this we can use asymmetric bootstrap program to bound this value, and I will explain this in detail at the end of the talk. Also, what we saw is that for the graviton-dilaton scattering, we are able to see that what exactly the delta C minus delta A counts along the RG flow. It turns out that it basically is related to some massive spinning states in the quantum field theory along the RG flow, and how precisely this captures this massive spinning state can be studied using some dispersion relation starting from this amplitude. Okay, so this is kind of the motivation.
May I ask a question?
Sure.
So what is actually the property of your CFT or QFT, which is translated into unitarity of these scattering amplitudes? Dilaton and graviton, whatever, they are kind of external.
Exactly. So like I'll consider that the QFT, like the spectrum of the QFT or whatever the quantum field theory, that is unitary, and these dilatons and gravitons are just probing this like quantum field theory. So the unitarity property is not about the dilaton or graviton theory, it's about the quantum field theory itself.
Okay, I guess my question is that this scattering amplitude, you can relate it to some correlators of
exactly
in your CFT, and that translates into certain properties of these correlators, right?
Yes.
But it's kind of implicit and it's not clear why.
Exactly. Yeah, I can tell you, even like what happens is that like this take this 4-dilaton amplitude, like suppose at any point on the like it's not have to be at the IR fixed point, like at any point on the RG flow, it can be related as a combination of like 4-point trace of the stress tensor, 3-point trace of the stress tensor, and 2-point trace of the stress tensor correlators in some particular combination. But then in terms of these correlators, it is not obvious how unitarity works. Like it is obvious from the 4-dilaton scattering amplitude, but it is non-obvious in terms of this set of correlators. Like we tried this thing, and yeah, I don't have really an answer to this question, but we were thinking at some point that how this unitarity translates in terms of correlators, and we don't have an answer yet. But it must have some relation.
Yes,
this has not been
explored. Because this is a priori, this is kind of assumption, because it's not completely obvious why that should be the case. Anyway, yeah, thank you much.
Yeah, I agree. Like from this, so that's why possibly this recent, if you followed this recent proof of Hartman and Mathis, where they proved this ANEC to prove the A theorem, there it is more clear interpretation why like this like how the unitarity plays, or this ANEC condition plays a role in proving this theorem, where this is more clear than from this background field method. It can, yeah. Can I proceed now?
Yes, thank you.
Okay. So yeah, so these are kind of the motivation or kind of the rough picture which I'm going to speak about in this talk. So let me first give the outline of my seminar. So first I'll start from very basics, like what are the trace anomalies in a conformal field theory. Then I will introduce this proposal of introducing background field method to like probe these trace anomalies along RG flow. Then I will like compute some observables starting from this effective field theory, and then test this proposal in some like RG flow examples. Then I will provide this dilatons and gravitons some dynamics to compute the scattering amplitude. And then I will show one example of asymmetric bootstrap application and some outlook for future. So let me first describe what are the trace anomalies in a conformal field theory. Maybe this is known to many of you, but just for comprehensiveness, let me try to explain it. So we consider a like conformal field theory, which is Weyl invariant when we put this like or conformally couple this theory in a background. So okay, maybe let's start with a conformal field theory, and we put this conformal field theory in a background geometry such that it is Weyl invariant. And this may need in general some particular kind of non-minimal terms depending on the which can depends on the curvature of the background, but this is just needed to make this theory Weyl invariant in the curved background. Okay. And then what I am telling, the Weyl transformation is basically nothing but basically a space-time dependent scaling of the metric, which is g mu nu goes to the power 2 sigma g mu nu. Sigma is the Weyl transformation parameter. And on top of it, all the local primary operators of the CFT will also transform depending on their scaling dimension, which is denoted by delta O. And then in a Weyl invariant theory, classically, the trace of the stress tensor is vanishes, which basically follows from if there exists action in the curved background. So basically this is invariant under Weyl transformation will imply that the trace of the stress tensor vanishes. But this is a classical statement. Now suppose we defined a partition function or a connected functional, which I am denoting by W, after integrating out all the CFT degrees of freedom, which is denoted by phi. Then we can start from this connected functional, and we may think that okay, under Weyl transformation maybe this is invariant, but it turns out to be it is not, because there is no Weyl invariant measure in general, and one can able to construct in terms of this background field what will be the variation of this connected functional, because it is proportional to the 1-point function of the stress tensor. And this basically appears because there are some UV divergence if you try to kind of compute this path integral, and you need to add some local counter terms, which basically violates this like Weyl symmetry. So this variation have to be local, and you can able to construct what local functional in terms of this background metric you can construct, which has dimension 4, and it turns out that it is like given by two numbers, a and c, and this a is the coefficient of the Euler density, which is a combination of particular curvature tensor square, and this Weyl square is also a combination of particular curvature tensor squares. In general, this statement is actually a scheme dependent statement, because you may add some term which is like some box of R, but that can be removed by choosing some special counter terms. So so here just let me tell that this A and C anomaly are two different kind of anomalies, and this can be seen if you put this sigma, which is the Weyl transformation parameter, to be a scale transformation, which is it's independent of the space-time point. So it's like some constant. Then you can see E4, which is the Euler density, which basically becomes a topological term. So in a non-compact space-time, this vanishes with some proper boundary conditions. It vanishes and the Weyl square survives. So that is why this Weyl square term, or the C anomaly coefficient, which is known as the scale anomaly or some type B anomaly coefficient, and this A is some Euler anomaly, or it's called also type A anomaly. And it was known, or like has been proved by convolutional non-perturbatively, is that this A monotonically decreases, but C don't have any monotonicity. Even there are counter examples where C can increase in energy flow. So this is a statement up to now just in a CFT. Now, how this A and C are related to flat space CFT, which we started from, and this can be shown if you just study, say, 2-point and the 3-point stress tensor correlators. So, for example, the 2-point stress tensor correlator in a CFT is given by some tensor structure times the central charge. And if you study the 3-point stress tensor, it is given by like 3 independent tensor structures and 3 numbers, which are written here as A, B, C. And it turns out that if you start with these correlators at separated points and then try to study the coincident point limit using some differential regularization, you can able to see that actually these OP coefficients are related to the A and C coefficients, which I mentioned in the earlier slide, which basically like are given by some like when coincident, like if you take some 3-point stress tensor, for example, starting from this expression, if you vary with respect to metric fluctuation in the right hand side, you can read, say, 3-point function of stress tensor, and from there what you will be able to see that if you like this, then it will be given by some 2 delta functions in the right hand side, and basically it contains the contact terms, and in that way you can able to relate this A and C anomaly coefficients to the OP coefficients appears in the stress tensor. So basically this A and C, they are the anomaly coefficient, but those are nothing but a linear combination of OP coefficients appears in the stress tensor correlators. And to note that this C anomaly is also proportional to the central charge, which also appears in the 2-point function, which is basically can be like read off this relation just using conformal order identity. Okay, so this is all about, I want to just review the CFT trace anomaly. So if you have any question, you can ask here.
I have a question. Can I ask a question? How do you find the remaining, the third coefficient? So from A and C, you determine 2.
Right. Yeah, somehow what happens is that if you start with this separated point 3-point correlator and suppose use this differential regularization to find the coincident limit when x1, x2 and x3 both are coinciding, it appears that only these 2 combinations appears as multiplication of delta function. The other coefficient somehow, or other linear combination of this coefficient somehow don't contribute to the fully contact piece of this correlator.
So there is one parameter remaining arbitrary in the OP.
That's true.
Okay, thanks.
That's true. Yeah, which maybe only is there for the separated point correlators, but not for the fully contact part. Okay. Now let me describe how to introduce this background field method in a renormalization group flow. So the way I already explained, the way we think quantum field theory is basically we start with some UV CFT, which has degrees of freedom. Collectively I am denoting by phi, and we put this in background metric G mu nu so that it is Weyl invariant. and then we deformed the theory by some like relevant operator, which I'm denoting by a set of relevant operators by OI, which is scaling dimension less than 4. And mi is at the mass scale where we deform the theory, and lambdas are basically the couplings of the deformation. Okay, so this is the quantum field theory. But now this deformed action is not Weyl invariant, and so the trace of the stress tensor is non-vanishing. So if you just take variation with respect to sigma, you will find that it is proportional to the set of deformation operators. But we want to restore basically this Weyl symmetry even for the deformed theory classically, and this is where we want to introduce this compensator field omega. Okay, so basically you can think of that we make this mass scale mi to be a space-time dependent mass scale, and the way to do that is basically we shift each of these mass scales mi by introducing a field called omega, which we call the compensator field, so that now if we demand that this omega transforms like under Weyl transformation like e to the power minus sigma times omega, it is easy to see now the compensated deformation is Weyl invariant classically. Okay, because omega transforms e to the power minus sigma or transforms the way I already explained, and as a combination you will see that it is now like Weyl invariant. So now again classically the trace of the stress tensor vanishes. Okay, and again like we will use some different parameterization for this omega field, which is omega is like e to the power minus tau, where this tau is basically coincides with this dilaton field for the spontaneous symmetry breaking case, like when it is a like Goldstone boson in general. So we basically will use tau as also the same name as the dilaton field. And basically this Weyl transformation property basically tells that this tau field is basically has this symmetry that okay under tau basically goes to tau plus sigma under Weyl transformation to make this action invariant. And here just to mention that actually from this expansion you can able to see that at linear order tau basically acts as a source for the trace of the stress tensor, like the metric fluctuation acts as a source for the stress tensor itself. This tau is basically a source for the trace of the stress tensor in the deformed theory in the QFT, which is compensated. Okay, so it's nothing but a extra source we introduced on top of the metric fluctuation. But now we can start with this compensated quantum field theory, which has now the fields like the CFT degrees of freedom, the G metric, and this compensated field omega, and integrate out the CFT degrees of freedom and define a connected functional for this compensated theory, which is a functional of the metric and this compensator field. But now classically, since this action is invariant, so if we take this theory and suppose go to like again the coincident points, then again like all the singularities of any observables will still be determined by the UV CFT. In a sense, what I'm trying to tell is that if we take this connected functional and do a Weyl transformation, it will still be given by the anomaly coefficient of the UV CFT, like the AUV and CUV times the E4 and the W square coefficient as it was for the CFT, because classical breaking is already compensated. But now we also introduce another background field omega, or the tau field, which basically is a source for the trace of the stress tensor. So there may be some terms in this while like this in the Weyl variation of this connected functional, which probes some different singularities of the operators. Like earlier this E4 W square, the A and CUV were probing the trace of the stress, like the stress tensor correlators kind of singularities or the coincident point. But now since due to this new source field tau, there may be some additional singularities of different operators, like the deformation operator 2-point 3-point function singularity. So there could be another some extra anomaly coefficients, which we will denote by this coupling space anomaly. So one can actually classify this coupling space anomaly, and it turns out that only for integers dimension operator in the UV CFT, their coupling space anomaly is present, and those are kind of an analog of the same type of C anomaly, which is a scale anomaly, appears as a W square. But those can be written in terms of this omega, like in terms of this new source field omega, and we already classified all such possibilities appears. And for the sake of this talk, I'll ignore this appearance of this coupling space anomaly. Okay, but you can ask me at the end how we can use background field method to probe them as well.
Is that is that kind of analogous to what you mentioned before, that in the trace you also have box of R term which you can cancel by local counter term, which is R squared?
Right, but these cannot be cancelled by using local.
But these are also local in terms of this external field omega, right? So these are local terms. So they will be non-local if delta is not integer. I'm just trying to understand the meaning of what you were saying about this extra terms in conformal anomaly. So you're just saying that there are extra structures which you can build out of omega, right?
Yes. So what happens is that if those are not integers, then basically, like in the connected functional, they contribute to some local terms, so you can remove by adding counter terms. But what happens is that in general, so I'm writing here the variation of this connected functional, but if you try to compute the connected functional for integer dimension operators, then basically it will have analogous structure like what I wrote this here, but in top of it there will be some log of box, and this becomes non-local only when deltas are integers.
Okay.
And this log of box under Weyl transformation basically gives sigma times this coupling space anomaly which I wrote. And those cannot be removed by adding local counter terms.
Okay, thank you.
Okay. Now, so the claim is that now for the compensated theory along the full RG flow, the anomaly are still given by the UV CFT anomaly coefficients. So now let us go to the extreme IR and integrate out all the massive degrees of freedom and try to write a effective field theory in the IR. So suppose the IR action then will be denoted by like some obviously IR CFT action, which will be also like the functional or function of the IR CFT degrees of freedom and the background metric. Then due to this massive particle integration, there will be some like effective field theory in terms of these background fields, which are tau and g mu nu. Here you see that I am writing tau instead of omega because now we are integrating out the massive degrees of freedom. So omega will be not expanded about omega equal to 0, but omega about 1, because we scale mi to be mi times omega, which is e to the power minus tau. And then there in principle could be coupling between the IR CFT degrees of freedom and also these background fields like tau. So, and these are basically I'm only writing these relevant terms, but there will be also irrelevant terms which in the energy scale below this mass gap of the theory, we can ignore. Those are irrelevant terms. So here I am just writing the possible relevant terms. Okay. So first of all, what could be the general structure of the interactions between the dilaton graviton and the IR CFT degrees of freedom? So that can be very easily classified, so the principle to classify them is that since we already reached in the IR CFT, so there cannot be any term in the action involving relevant operator of the IR CFT which remains or will be non-vanishing in the flat space, unless that will again generate a RG flow. That means we never reached the IR fixed point at all. But then you may think that, okay, then I have to possibly introduce curvatures to construct such kind of terms if there are some relevant operators. But then again, you can think of writing down some spinning operators by contracting with some Riemann tensor or the Ricci tensors. But it turns out that the unitarity of the scaling dimensions will make sure that this kind of terms, if you introduce spinning operators, those will always be irrelevant terms. So the only relevant terms, it turns out that it only have the scalar operators O, delta, and with the Ricci scalar R. Okay, and the scaling dimensions of the operators which can contribute to relevant terms runs between 1 and 2. Okay, and here let me mention the notation. So G hat metric I am denoting by e to the power minus 2 tau times G mu nu, and which is basically conformal invariant metric because G goes to e to the power 2 sigma and tau translates to tau plus sigma. So this is a conformal invariant metric G hat, and O hat is again a conformal invariant combination of the the scalar operator of the IR CFT, or the scalar primary operator of the IR CFT, which will be denoted by e to the power delta tau times O. And these are the only relevant terms I can have with the scaling dimensions between 1 and 2. Now, once we have this IR action. Obviously, we have not given the expression for the EFT, which you have to find. And to do that, basically, again, you just try to integrate out the IR CFT degrees of freedom and try to find a connected functional. And again, the connected functional, the total connected functional, the variation will be still given by the same AUV and CUV. But now the IR CFT will generate a new anomaly and the same kind of structure, same kind of anomaly like the UV has, but with the defined coefficient. Let's call them AIR and CIR. That means since this term actually integrated out won't generate any anomaly, it's invariant. It turns out that this EFT, the variation of the EFT action, have to take care of the difference between the IR CFT and the UV CFT anomaly. That is the fact that if you do a Weyl transformation of the EFT action, it should contains the coefficient of E4 to be delta A, which is given by AUV minus AIR, and delta C, which will be given by CUV minus CIR. And if you solve this equation, and this is done nicely by like starting from Rygaard and some other papers follows by introducing a local field tau, and the solution is basically can be written as sum of three terms. Obviously, there will be some terms you can write which is invariant under Weyl transformation, so you have to construct out of the G-hat combination, and you just write whatever you can write as a general coordinate invariant way. Like constructed out of this G-hat metric, and these are given by some parameters like 0th order lambda, 2 derivative order R0, and a 3 derivative order some R1, R2, R3 coefficients. But these coefficients are in general not fixed, and they will depend on the details of the RG flow, what particles you integrated out at which energy scale. It will depend on many other things. But the demand is that the variation of this AEFT will be given by delta A times E4 and delta C times Weyl square. Basically tells that the variation of this AA action, which is which appears as a coefficient of the change of A anomaly, should be sigma times E4, and that one can see just if you start from this expression and take a variation, basically tau going to tau plus sigma. So naively it seems that it produces sigma E4, but since E4 also transforms, so we need some more term to compensate the variation of the like under Weyl transformation how E4 transforms, which basically needs all this set of terms. And for the Weyl square term, it is easy because square root G Weyl square is invariant. So basically tau going to tau plus sigma basically generates this term. So this is basically the solution, and this is the effective field theory, which will be our starting point to compute observables. For example, but okay, to do that, sure.
You know, what is the meaning of the first argument on the left-hand side? What is this phi, and how is it related to, well, roughly speaking, these operators O's, O delta? Is it just composed of phi or what?
Yeah, in general, in a non-perturbative CFT, I don't know what those are, but suppose this IRC, like for example, like take like for in string theory, like take these x mu's are basically some scalar field on the world sheet, and then you know the vertex operators are basically kind of the primer is constructed out of e to the power ik dot x. So in a like this kind of theory I know, or maybe in a like free field theories or generalized free field theories, I can able to write this O delta in terms of phi's. But in a non-perturbative theory, I don't know how to write them in terms of this degrees of freedom of the IR CFT phi in general.
Because in my opinion, the argument phi, this is the background value, background matter field, as I understand. Yeah.
No, these phi's are basically I'm denoting by a collective degrees of freedom of the IR CFT. I don't know what those are, and in general, I don't know how to write this O delta in terms of these phi's. Only in the weakly coupled CFTs I know.
Okay, but what I want to say that this effective field theory part,
yes.
AEFT,
yes,
it should also depend on phi generally.
That's
if
true.
You have some non-vanishing mean field phi, then this effective field theory contribution will also depend on phi.
Very good, very good. So this is what I am trying to classify here. So I agree that it in general depends on the phi, right? And this is like but in a CFT, the way I think is that given by like CFT, at least non-perturbative, the way we define in terms of bootstrap are given by some set of operators, some scaling dimension OP coefficient. Now, given a set of operator, we can try to see what we can write, right, in terms of these operators O, and this is what the full classification we can write here. Then we have a EFT, which is completely decoupled. Like I'm defining, you can call this full thing to be EFT. This is maybe it's like the way I am trying to tell. Maybe the full thing you can call to be EFT, and I am separating it. The EF, like the dilaton degrees of freedom, which can interact with the CFT to be, I am like trying to write in a separate term, and then a EFT I am denoting by just which depends on the background fields, no CFT degrees of freedom.
Okay, maybe I will rephrase my question in somewhat different way. Sure. Suppose you have a phi to the 4 conformal field theory, phi to the 4 linear interaction, right? Mm-hmm. Then you know very well that one loop conformal anomaly will have a contribution proportional to phi to the 4.
Okay, that's true.
So then the question is, where this piece is contained, in which part of your equation? Because this effective field theory, AEFT, I think it should also contain this phi to the 4 piece.
So you are considering, just to clarify,
marginal operator, it does not involve any M that you have on the right hand side, the third term.
Right, but this phi to the power 4 theory you are considering in 4 minus epsilon dimension, and then you are telling that okay, like the trace of the but that I think is contained in my AIR, right? So I have this IR CFT, right, and I can starting from this IR CFT I can integrate it out the 5 degrees of freedom and can write a connected functional, and the variation of this connected functional will produce me some 1-point function of trace of the stress tensor, and that one loop contribution will contain the IR CFT anomaly given by the AIR value, which possibly you are telling the one loop correction, the AIR. So it is contained in the AIR CFT or the coefficient AIR here and the CIR here. Maybe I don't know. Is this what you think, or I am making some wrong statement?
Well, I don't know. Maybe you would just proceed further. Thank you. Thank you for your response. Yeah.
Okay. Yeah, this is kind of my understanding, but yeah. Okay. So now what I'm going to describe is that starting from this effective field theory, we can compute various vertices, scattering amplitude. Okay, first let's compute some vertices involving these graviton-dilaton fields and see whether, like, how they are like determined by this theory independent like by the RG flow independent parameter delta N and delta C, and the RG flow dependent parameters like the lambda R0, R1, R2, R3 first. So to do that, we again kind of do a field redefinition of this tau dilaton field in terms of this phi. So the exact relation is e to the power minus tau is 1 minus phi over square root 2f. So f, for a moment, it has a mass dimension, but for now you can consider basically 1 over f counts the number of dilatons in any of the vertices. Okay, so we are not giving a physical meaning, it's just a mass dependent parameters. Then we can also expand the background metric about the flat metric and some Planck length kappa, and you can again think this kappa basically counts the number of gravitons involved in any vertex. And we will consider the graviton field to be traceless and transverse. So this is kind of our choice to like whatever we can choose for the background fields, and we are just choosing that we will probe by traceless and transverse gravitons. So then we can define the vertices involving graviton-dilaton fields starting from this effective field theory and varying as many number we want with respect to the graviton and dilatons in momentum space. And what I am going to like what we computed is that the 3 dilaton vertex, the 1 graviton 2 dilaton, 4 dilaton, 2 graviton 1 dilaton, and 2 graviton 2 dilaton vertices So obviously all of them are not needed to compute delta or read of delta, delta C, R0, R1s, but those are needed up to the end to find the full amplitude which we are interested in. So for example, if you compute 3-dilaton vertex, in general it turns out to be depends on the delta A, which is the change of the A anomaly, but it also depends on the one theory dependent parameter R1. So okay, for a moment here I am only showing the 4 power of momenta contribution to the vertices. Okay, at like in the low energy expansion, only at the 4 power of momenta. And the way you can think of is basically these blob vertices are the EFT vertices. In a sense, inside the blobs, like there are, like in perturbatively you can think there are loops of massive particles which you integrated out, and this is given by a low energy, like it's a low energy expansion of the full vertex. And so this is the 3-dilaton vertex, and if we for a given RG flow we can like inside this blob we can integrate out the massive particles, and we can able to compute this vertex and compare with this expression, and we can read of this various anomaly difference and this R1 coefficients. Similarly, we can compute one graviton-dilaton vertex, and this one graviton-dilaton vertex, if we compute, it turns out to be, it also depends on this delta A and the theory dependent parameter R1. So yeah, just the purpose of showing this vertex is basically, you may have seen recently that Hartman and Matthews proved the A theorem using the NX sum rule. And this NX sum rule, what they basically considered is basically they considered the null energy radiated like part of the stress tensor, which is the TUU component, and basically that is inserted between the states created by the trace of the stress tensor. And then basically there are some smearing, and you just compute some null energy at the end, and this is positive given by the NX. And it turns out that it can be related to our this vertex, which is basically, you can think of this one of the graviton is like the T mu nu, which the TUU component if you take, and these dilatons I already mentioned, these are basically source for the trace of the stress tensor. So in general, like we find a relation that okay, if you take our vertex and operate this like projection operator, which basically translates to their like this NX like operator, and it also reads of the delta A coefficient here, and then NX can be used to prove that A theorem starting from this vertex as well. Okay. Now so obviously up to now we only probe the delta A, and it's like okay, it's like there are Oizumi consistency conditions and all these things which tells that like A is monotonic and it's independent of any of the parameter, like any of the scale like mass dependent parameters of the RG flow, so it should match even from the EFT in the IR. But there are some confusions in the literature that why the C have to also match between the UV and IR, writing down this effective field theory. So it's better to find some observables where this delta C also appears and test this in examples to make this like the C anomaly matching to make statement to be more concrete. And one such kind of simple observable is basically this 2 graviton 1-dilaton vertex, and contracted with the polarizations for the gravitons, and it is given by some 3 tensor structures with 3 functions f1, f2, f3. And one can start with this FTX and find this f1, f2, f3, and which contains both delta A, delta C, and this R1 coefficient. At 4 power of momenta, one can compute the other powers of momenta up to 4 also. But the thing is that now in a given example, if we can compute this thing, just comparing different tensor structure, it is easy to read off what will be the change of the delta A or the A anomaly, what will be the change of the C anomaly, and this one observable is enough to compute like all the coefficients in general. So you can see that here R2 or 3 coefficients are not appearing, and they basically R2 only appears in only when observables involving only gravitons, and R3 never appears because it's a Weyl density, so it's a total derivative term. So these are kind of the observables which I'm going to test in few examples in my later slides. So let's start with testing a very simple, like testing this proposal in a very simple RG flow, which is in the UV, take free massive scale, like free massless scalar theory, and then do a deformation by the mass term. Okay. Now it's a mass term deformation, so obviously there is a mass gap m, and then when we flow to energy smaller than m, there are basically no degrees of freedom left, so the IR CFT is empty. So in the IR there is no anomaly, so AIR and CIR are 0, and it is known that the free scalar AUV and CUV are given by some numbers. So this is a good good example where we can compute this vertices and can see that can we reproduce this AUV and CUV numbers. So basically this is the action for the QFT, which is given by this kinetic term in the flat space, and then this is the mass square deformation. Now we can put this theory in a curved background, which needs to introduce a particular non-minimal term r pi square with a particular coefficient. But then we also need to compensate the Weyl symmetry breaking in the curved background, which basically tells that we have to shift m to b to the power m times e to the power minus tau, which is basically compensating. Now we can start from this action and compute, say, 2 graviton-1-dilaton vertex which contains all the anomaly coefficients, and it basically involves summing 2 one-loop diagrams, and we can from there we can compute different coefficient of different tensor structures in this vertex. And what we found, and comparing with our prediction from the EFT, we can see that we can read of the correct AUV, CUV values because the IR values are 0, and also this R1, which is a EFT parameter not determined by the anomaly matching. So this basically tells that, okay, like when there is a IR CFT is kind of empty, our prescription works even for the C anomaly computation. We did the same thing for the free Dirac fermion case, and it also involves some set of diagrams, and it also produced the correct result for the A and C coefficients for the Dirac fermions. Now let me try to tell, all these examples, our IR CFT was trivial, empty. So maybe it would be good in the case where the IR CFT is non-trivial, and to find such kind of example, we worked out in the case of weakly relevant flow. So what is a weakly relevant flow? So suppose there is a UV CFT which has an operator whose scaling dimension is very close to 4 but a little below, and the scaling dimension is given by 4 minus delta, where the delta is much less than 1 but positive. Then what happens is we can write the quantum field theory just by deforming by this weakly relevant operator and treat this lambda 0 to be a perturbative parameter. We can do some one loop renormalization. In general, there is no divergence, but the renormalization means here basically is that if we continuously move this or continuously make this delta to be close to 0, still our renormalized observables in terms of renormalized couplings are finite, which basically gives the particular wave function renormalization and the beta function. And for example, if we compute the one loop beta function for this theory, it turns out that this is given by minus delta lambda. Lambda is the renormalized coupling, and delta is the difference between the space-time dimension and the scaling dimension of the operator. And at one, this is the classical actually the beta function, and then at one loop it contributes at lambda square, which is given by the OP coefficient of the deforming operator, like 3-point function COO, and omega 3 is the sphere volume 2 pi square. And you can see there is a sign difference between the classical beta, the classical contribution and the one loop quantum contribution. So in general, we can find a coupling value where this beta function vanishes perturbatively. And such kind of a perturbative fixed point exists for the coupling, which is given by lambda star, which is given by 2 delta over COO times omega 3. And when this delta is much less than 1, you can see that this lambda star is also small. So we can use perturbation theory this is a short flow, and we can use perturbation theory to study this example. And we have a full control over it, and possibly we can able to compute this delta n and delta c value for this example and test our proposal. So we take this example, and then we use our proposal that we compensate by scaling this m0 times omega, and then again expand about flat background and expand about omega equal to 1 in terms of this dilaton field. There is some way also starting from the renormalized action and do this, but what happens at the end is that if we want to compute, okay, now we start with this action and then try to find the EFT action by integrating out this CFT degrees of freedom, and it turns out that the part of the EFT action which contributes to the 3 dilaton vertex at leading order in this coupling is given by the 2-point function of the deform operator, which basically contributes the cubic order in phi, which contributes to the 3 dilaton vertex. And similarly, if we want to compute the contribution which contains 2 graviton, 1 dilaton, it is given by the 3-point function of the stress strength, like 2 stress tensor and 1 deform operator in the quantum field theory. Note that all these are quantum field theory correlation functions. So this can be seen just starting from this expression and just expanding about lambda 0 after substituting this compensated action. So the goal will be to compute then these QFT correlators for this theory and substitute here and try to extract the 4th derivative power of the action, which contributes to the 4 momenta power to these vertices. So the simplest one will be to compute the 3 dilaton vertex, and this turns out to be one can do a derivative expansion of the fields, and 4 power of momenta it will be given by, like, this is the action and given by the single integral L1, and L1 involves 2-point function of the QFT. To evaluate this 2-point function of the QFT, it's not like that difficult, because we know the beta function and we know the anomalous dimension, so we can basically have to solve the Kalan-Simanjik equation for the 2-point function. And the Kalan-Simanjik leading log or the leading radial behaviors can be resummed, and it is given by this factor here. And on top of it, its initial value have to be computed. This leading resummation factor is given here, and then the initial value of the solution of the Kalan-Simanjik equation have to compute using conformal perturbation theory, and in leading order lambda it has been computed here. And now this full expression, if we substitute and integrate over the space-time points y, and then compare and go to the momentum spaces and compute 3 dilaton vertex, from there we can see that we can compute this delta A value, which is proportional to delta Q over COO squared. Okay, and also we can read of R1 as well. So just to mention is that it is very important to resum this radial behavior using Kalan-Simanjik equation. If you just use, suppose just use the conformal perturbation theory to compute this QFT, since this conformal perturbation theory value is very valid very near to the UV fixed point, and if you go to large distance, it actually won't work, and there you will see that for that reason there will be some IR divergence in this integral. So this resummation is very important, and once you do that, everything is finite. One can compute this delta A value, which is given here. And this actually agrees, like this has been computed earlier by Klevanov, Pupu and Sabdi using some free energy computation on the force sphere, and it agrees with this computation. So basically this tells that this background field approach works. We can also compute the now for the computation of delta C, as far as we know earlier, no one computed for this example even directly how the delta C computation works, but it's kind of easy, because if we want to compute because what I mentioned earlier is that the C anomaly is proportional to the central charge which appears in the 2-point function. So in general, if we directly compute this, we can start with a QFT 2-point function, and since there is no anomalous dimension for the trace of the stress tensor, so we don't need any Kalan-Simanjik resummation. We can just use conformal perturbation theory and then go to the IR, basically by substituting the IR coupling and taking the distance scale to be large compared to this deformation length mass scale m0. And then we can compute the delta C, and it is proportional to small delta, and you can see the delta A was delta Q, but delta C is linear in delta, so it's more prominent. And then this computation, direct computation, now again we can use this effective field theory and solve solution of Kalan-Simanjik equation, and from there we can also compute this value, and it agrees. Okay, so this basically makes that this delta C, which is the C anomaly coefficient, also can be proved using our vertices, and this anomaly matching also works for the C anomaly, because this is a kind of very non-trivial example. Okay. So is there any question up to now? Yeah, please feel free to stop me at any point, because maybe I'm going a bit fast.
By the way, do you have how many slides do you have?
I think I need around 8 to 10 minutes maybe. Is it okay?
Okay, it should be fine.
Okay, so now I just showed the vertices involving various graviton-dilaton thing. Now I want to provide some dynamics to the graviton-dilaton and compute some scattering amplitude, which will be useful for the S-matrix bootstrap perspective. So to do that, what we assume is that we want to break the Weyl symmetry at a scale below the Planck scale. And this is usual, like if in nature, if there are some Weyl symmetry was there, obviously we assume that the breaking has happened below the Planck scale. And to do that, what we did is to give a kinetic term for the phi dilaton field. We introduce this kinetic term in a Weyl invariant way. So, and this can be done by basically writing down a action in terms of the metric g hat, which involves this dilaton, which basically you can think of it's almost same as the almost same like the conformally coupled action for a scalar field phi. But there are some extra terms, which is basically these two terms, which basically comes from the expanding of this RG head, and this is a conformally invariant part. And now you can see there is a term which is R phi, which basically mixes, or like it's not fully, this action is not fully diagonal in graviton and dilaton field. And there is a term which is just a Ricci scalar. So now we considered the graviton action to be given by the Einstein-Hilbert action, but we added this f square by 6 term just to cancel this extra part. And once we consider the limit when the Planck length goes to 0, kappa is when the Planck length goes to 0 and the f goes to infinity with the limit that kappa is much less than 1 over f, so the conformal, the Weyl symmetry breaking is much below the Planck scale, and this is the decoupling limit what we will consider. So first we will take the Planck length to be 0, then we will take the 1 over f scale, which is the Weyl symmetry breaking scale, to be 0, and this is the consecutive limit which we will consider as a decoupling limit to compute our observables. So basically we will start from our EFT action, and with EFT action and the like the coupling between the dilaton graviton with the CFT, and we add these kinetic terms, and this will be the full action with which we will start computing amplitudes. And it turns out that if we consider the dilaton field, like the equation of motion for the dilaton field from this action, which is given by the massless condition, or all the dilatons are on cell, actually this contribution vanishes. So it's enough to start with the EFT only and use this equation of motion follows from the dilaton action and put everything to the background metric. And this is actually what has been done by Komorgowski and Swimmer. And what they have seen is that they have computed the 4 dilaton amplitude at 4 power moment. It is proportional to delta A times this square plus t square plus u square, right, which are the Mandelstam variables defined here. And you can now write a dispersion relation, assuming that like at high energy, like there is some like at s going to infinity, the R contribution vanishes, or it is like suppressed. Yeah, this it's called this CRG conjecture, which is the classical Rege growth conjecture. And then you can use this and try to write a dispersion relation for the delta A, and what you will see is that it is proportional to the imaginary part of the forward limit of the scattering amplitude, which is proportional to the cross section, so it's positive and known as the A theorem. So we can play the same game with for the graviton-dilaton scattering amplitude, and in the decoupling limit the leading order is given by the kappa square term, and which turns out to be independent, like it's just receives contribution only from the kinetic term of the action. Don't probe any of the RG flow, so not much interesting. It is just the usual kind of follows from the Einstein-Hilbert and the coupling to the dilaton system. But at the subleading order in the decoupling limit, which is kappa square over f square, we can compute, and the blob vertices are basically probes this like RG flow, which I already showed earlier as the vertices follows from the EFT action. And then individually these diagrams also actually knows about how this dilaton couples to the IR CFT degrees of freedom, various contributions which are denoted by these lambda delta parameters, and also these theory dependent parameters R1. But once we sum over all such diagrams, it turns out that all the theory dependent, like the RG flow dependent parameters like the R1, as well as this how this IR CFT couples to the dilaton degrees of dilaton graviton system, all this cancels out, and we are left out the dilaton graviton scattering amplitude is completely determined by the difference of the C anomaly and the A anomaly coefficient. And once we have this relation, we can check various things. First of all, we can check that in the forward limit what happens when graviton dilaton going to graviton dilaton, and in the forward limit this amplitude actually vanishes. So we don't hope that there is any kind of positivity or any kind of kind of C minus A theorem like here, but we still can have some interesting like output. So let's write down this graviton-dilaton amplitude, like considering, say, after putting some polarizations. For example, if we consider +2 graviton close to +2 graviton in the out state, then it turns out that it depends on the theory-dependent various parameters. But if we consider the helicity flipping amplitude, suppose we scatter a ingoing graviton to be +2 helicity and the outgoing graviton to be -2 helicity, it turns out that this part actually, so yeah, maybe I should mention here I am just writing the 4 power of momenta piece. There are also 2 powers and other powers are there, and those basically contributes to the plus part, but the 4 power of momenta only contributes to the +2 to -2, which is the helicity flipping part of the amplitude, and this is just given by delta C minus delta A times T square. And then we can try to write a dispersion relation for this combination delta C minus delta A, and what we saw is that it is given by some imaginary part of the 2 power of the momentum transfer square derivative of the amplitude in the helicity flipping amplitude in the forward limit. And now we can decompose this amplitude in the partial waves, and it turns out that from that we can see that this delta C minus delta A actually probes the spinning massive states which are partial wave spin greater than or equal to 2. So like this, it don't probe the scalar degree, like the scalar massive states along the RG flow. So this is kind of the observation we did from this scattering amplitude computation. Now in last 3 minutes roughly, let me try to only, yeah, maybe I won't give the details, but only show the results of the S-matrix bootstrap application. So here the setup we considered is that we considered a gapped QFT which has G2 symmetry, and we considered that the spectrum of this gapped QFT is G2 odd. This is just for the simplification. It has like just we have to consider less number of amplitudes, and then we asked the question is that what is the space of UV CFTs which can flow to a gapped QFT with a single stable particle which is G2 odd. In specific, we want to basically bound the a-anomaly coefficient of the UV CFT for this bootstrap setup. And to do that, it turns out that we need to non-perturbatively analyze 3 sets of amplitudes, like this M, I'm calling this gap particle. This is the scalar going to scalar amplitude, and 2 scalar going to 2 dilaton, and 2 dilaton going to 2 dilaton amplitude, because this is the only the G2 event sector. And then basically we use S-matrix bootstrap setup, which is basically a combination of Mandelstam analyticity, crossing, and unitarity. On top of it, there are some low energy behaviors of these amplitudes due to some soft dilaton theorem. And once we do that, what we found is that the main result what we found is that for this space of UV CFT which can flow to a gapped QFT with G2 odd massive stable particle, the minimum of this a-anomaly is basically given by 0.32 times the free scalar anomaly. So here the free boson anomaly, like we just multiplied by the free scalar anomaly coefficient here. So the free boson anomaly sits in 1, and the allowed region is here. And it is interesting that the earlier, like all this, okay, there is obviously no example what we can find which is the anomaly below the free boson anomaly. But also earlier all this kind of Komárowski-Swimer's unitarity proof and all these things assumes that the anomaly have to be greater than 0. But if we assume some spectrum, then we can see that it cannot go to 0. The minimum value have to be in this, like minimum value have to be given by like 0.32 times A pre. So this is the allowed region, and it can be up to infinity. So there is only a minimal like minimum for this AUV. Okay, so I can stop here if you want, or I can maybe take 5 minutes for the outlook. So it's on you. Sorry for going over time.
Oh, well, I think it's better if you make a quick summary.
Okay. Sure. So yeah, so basically the summary is basically what we did is basically like we followed some earlier constructions of this background field method and try to probe not only this a-anomaly coefficient but also how this c-anomaly coefficient changes along the RG flow. And in the literature there are some confusion whether this c-anomaly, because it is a scale anomaly, whether it will match between the UV and IR. And our claim is that since these anomaly coefficients are basically probes the fully connected part of the correlators, which are completely determined by the UV CFT data, so it should be same along the RG flow. So the anomaly matching should work also for the scale anomaly. And then to do that, or to make it concrete, we introduce background field method and compute some observables in terms of this background field and show how they really probes different anomaly coefficients. And one of the interesting observation is that we saw that, like say, 2 graviton-dilaton amplitude basically probes, like it's completely universal at 4 power of momenta, the helicity flipping part, and it probes the particular coefficient delta C minus delta A and independent of the details of the RG flow, and it probes the massive spinning states of the CFT. And in a sense, you can think of is basically if you create a QFT state by like operating the trace of the stress tensor on the vacuum and send a shock wave through it and see the helicity flipping part of the shock wave, it is completely universal for any QFT and it is given by just the UV and the IR CFT anomaly coefficient. So this is kind of the main summary of my talk.
Okay, thank you. Are there any questions?
So would you expect similar relations in 6 dimensions?
Okay, so what happens is that we actually played with the 6 dimension because you know this Elbang and maybe so in 6 dimension this Elbang and Myers and Tyson, many other people, they constructed this EFT action in 6 dimension. So obviously they don't have the full action because they don't have the terms which are like which describes the coupling between the IR CFT and the dilaton graviton system, but that can be constructed. And then starting from this full action, we can try to see whether what happens is that if you compute 4 dilaton scattering amplitude, this a-anomaly appears as a STU coefficient, which is 6 power of momenta to the amplitude, which is proportional to STU. And if you take forward limit, it vanishes. So, but you can still try to write a dispersion relation. And it turns out that the dispersion relation, using dispersion relation, you won't be able to prove a theorem. So then we tried to see whether now we can compute this graviton-dilaton amplitude and see what can it happen. It is interesting that there are 3 C anomaly coefficients, and this graviton-dilaton amplitude is again independent of all the C anomaly. Like it is independent of, like in 4 dimension, it depends on a combination of delta N and delta C. But in 6D, it turns out to be completely independent of the C, 3 of the C anomalies coefficient, and as well as the theory dependent parameters. It again given by delta A part. So there we were hoping that maybe we will be able to see or prove a theorem starting from this. But again, when you take the forward limit for the graviton-dilaton to graviton-dilaton scattering amplitude, it again vanishes. So what we found is that actually there is, at least even using graviton-dilaton scattering, we don't have a theorem for that as well. So this is kind of the current status, and yeah, it's not clear that from the scattering amplitude or the background field method we can able to prove a theorem in 6D, or even I don't know whether there is a theorem in generic RG flow. Maybe some supersymmetric theories there is also a proof, but not maybe in generic case.
May I ask a question?
Sure.
So at some point you discussed delta C minus delta A.
Yes.
As some integral.
Yeah.
Yeah. So what is the point here? Are you saying that right-hand side is positive?
No, right-hand side is not positive. So it's non-monotonic, this combination. The point here is that this combination delta C minus delta A, what exactly it probes in a RG flow. So what we observed is that it probes a particular set of spinning states which has like a particular state of massive spinning state in the RG flow which has spin greater or equal to 2. So
it doesn't tell us anything how C minus A grows along the trajectory or changes along that trajectory.
No, not like that. It's yeah, along the trajectory how it grows or anything, it won't tell. But this relation can be used to, for example, there are some counter examples where the C increases along the RG flow, and in maybe computing, like coupling this set of systems in this background field method, we can able to learn why exactly or what kind of states contributes to this RG flow, so that there is non-monotonicity, and for which kind of RG flow there could be monotonicity. So starting from here and analyzing this kind of different examples, we may able to learn or able to specify that this, or maybe able to find some conditions that for which kind of RG flow we can have a monotonicity and for which kind won't be. But yeah, I don't have a specific answer because yeah, I never looked at those kind of RG flow where this C, like in conformal Bang-Jakes theory, we started some point where actually the C anomaly increases along the RG flow in this perturbative example, and it would be interesting there exactly how things goes wrong in terms of this background field method.
I see.
But one interesting,
just an observation that, I mean, C minus A is just a coefficient in front of Riemann tensor in the anomaly.
Exactly, in a CFT. Good.
Yeah.
So you can think of this really is like a generalization of this CFT, but for a RG flow. So this is kind of one of the thing which we are thinking. So there are some set of papers where people observe that in a CFT, when you are on a fixed point, if you kind of compute, like count some specific set of operators in supersymmetric gas theories, or even it appears actually if you compute entropy of Schwarzschild black hole, some logarithmic terms. And it may be due to this fact that the trace anomaly, as you mentioned, that it's like the Riemann tensor square contribution is C minus A. But now start from the CFT and do a RG flow, and then basically we are kind of giving a proposal. Now if you want to see this change of the C minus A combination along a RG flow, possibly you have to see that you have to basically take this QFT vacuum and possibly send a shockwave and see the helicity flipping part, and that determines this change of this thing. And maybe it will be interesting to see in this all these specific cases, like for a RG flow, how things goes.
Okay, thank you.
Yeah, and another thing, maybe I don't know, like another thing could be is that in this Hoffman-Maldacena, like they are also this in a CFT, they also this A minus C combination appears, right? Which basically they use to prove this A over C bound in a CFT. Now, if we combine with our S matrix bound for a given spectrum, we have a bound for the AUV, and if we combine, we can get a CUV bound for the UV set of CFTs, which can flow to a gapped QFT. But this is a bit naive because this Hoffman-Maldacena bound is for generic CFT, and this bound is for gapped, for the space of CFT which can flow to a gapped QFT. But we think that it can be improved using like this graviton-dilaton system and use the S matrix bootstrap. Then we can be able to kind of find a improvement over this CUV from the bootstrap perspective.
Okay, thank you.
Any further questions? Okay, it seems that we don't have any questions. So thank you very much for a nice talk.
Thank you.
And thank you everyone for coming, and hope to see you next week.